be here. First of all, I should apologize that I'm not at all a specialist in liquid crystals. And the main idea of my talk was to speak a little bit about simple applications of invariant theory. Exactly on this subject, as David said, I worked for about 10 years with Louis Michel, who partly participated in liquid crystal activity also, but I was not touched with this kind of applications. And idea of my talk today is mainly just to speak about mathematical method, basic mathematical method related with invariant theory, and mainly related probably with another kind of application which I knew better than liquid crystal. I work particularly on molecular applications, on finite particle system, quantum system. And I'm mainly interested in description of some qualitative effects which exist under variation of some kind of parameters. This is system with finite number of degree of freedom, but some kind of phenomena which we can see are quite similar to what is observed in solid state or in liquid crystal, related with some kind of phase transition, with modification of system. And I try to give my presentation in some way, not looking too much into concrete physical besides these mathematical tools. And just I cite initially the Galilei phrase, which was exactly one of the favorite citation by Louis Michel, when he said that we need to use mathematics, and he did not like, by the way, the saying mathematical physics. He preferred to say that there is mathematics and we try to apply mathematics to physical problem, and we need to look at the physical background and apply some kind of mathematics. So today I will not speak exactly about physical background related with liquid crystal, but I think that probably for audience here it will be more easy to see if there are some kind of relation with what I do discussing the invariant theory applications. I try to start with some formal description, like we have some space of variables on which we can construct our model. In fact, I have in mind always some kind of molecular description, and this kind of variables can be phase variables, phase space variables, or variables describing some quantum system. But what is important is that this space of variables describe the system under presence of certain symmetry. I have symmetry group, invariant symmetry group of the problem, and these variables, which I will discuss, transform according some representation of this symmetry group. In the simplest cases, the representation will be reducible. In more complicated cases, it will be a reducible representation. But we can classify our variables according to representation of symmetry group of the problem. The most trivial example, if you want, this is just example of one variable x and the symmetry group of reflection Z2 symmetry group which act on the space of variables. It is quite clear that we have two kinds of object of function which are either invariant, which transform according to totally symmetric representation of this Z2 group or antisymmetric. And we can, for this kind of function, we can find example of symmetric function like x squared, and we can construct any invariant function as some kind of polynomial over this x squared. And or we can construct any antisymmetric function as product of x by any polynomial constructed from elementary symmetric function x squared. This is in some way idea that I will speak about polynomial invariant. And in this case, this is quite also trivial to see that we have polynomial like monomial like x squared, x4, and so on. And by the way, here I can encode this information in the form of so-called generating function. If I look this kind of development of this power series, this will give 1 plus t squared plus t4 and so on. And I will see that coefficient between this auxiliary variable t will give the number of polynomial of degree which can be constructed in these invariant polynomials. The same invariant polynomials will have trivial form here, and this will be t multiplied by this serial. This will be t plus t cubed plus t5 and so on. So this will be generating function for covariant, which can be constructed from this type of variables. This is one kind of analysis, and another kind of analysis which I will use is the group action on the space of my variables. What is the group action on these variables? One variable x in this simplest case. If I take arbitrary function, the group action will transform x will minus x. So this will be the orbit of Z2 action consisted of 2 points. And the generic orbit are always orbits consisting of 2 points, except if I will take points z equals 0. This point will be invariant with respect to group action. And so I can classify the orbit of the action by the so-called stabilizer of this point. That is by subgroup in general which leave this point invariant. In this case, generic orbit has trivial stabilizer, C1, nothing. Leave these points invariant. This 0 point has stabilizer Z2 group itself, so I can classify orbits by stabilizer, and I can go to the space of orbits. Instead of looking at the space of points, I can look at the space of orbits, and on this space of orbits I will have generic orbits with stabilizer C1 and one exceptional orbit with stabilizer Z2. So this is kind of stratification of this space. I have 2 different strata in this case. By the strata I mean the set of orbits which has the same stabilizer up to some kind of complications related with the symmetry, the conjugation of the subsymmetry group. Just to show less trivial example, but nevertheless rather trivial, let's look at the symmetry group of the cube. And we can consider the three-dimensional space around as a space on which the symmetry group acts, the symmetry group action. What kind of orbits we have? First of all, it is necessary just to precise what is the symmetry group. This is the symmetry group. Let's consider the complete symmetry group of the cube, which includes all rotation and all reflection. This is group of order 48. So if I will take generic point which does not belong to any symmetry element, the group will form an orbit of 48 points. In contrast, if I will take the point which is at the center, for example, this point will be invariant. So this will be orbit of 1 point with stabilizer equal the complete group. You see clearly that there are some special points which are situated on C4 axis, on C3 axis, on C2 axis, which go through this two middle of the edges, opposite edges. And there are points which belong to the plane but not to the axis. There are a lot of different orbits with respect to their stabilizer. So this is kind of description of the group action for this kind. And for example, we have C2 operation which belong to this group of two types. We can make C2 operation just by making C2 around this C4 axis. This is symmetry operation. But we can make C2 operation around this diagonal axis. And this is two different operations which belong to two different classes of conjugated elements. By symmetry operation, you cannot move one to another. But all axes which correspond to the 2 points going through opposite sides, these belong to the same class. So there's different classes of conjugated elements which form for some specific kind of groups. So for this general situation, the idea will be exactly the same. We will represent the space of invariant or covariant by the form of generating function, first of all, just by counting the number of invariant in each degree. Formally, this means that I will write like here this expression which show the number of tensors of this type of symmetry constructed from elementary tensors which span this initial representation. I use initial representation, and this is final representation. So starting from initial representation, I start object by constructing polynomial object which transform according to final representation, and I count the number of objects in any degrees, and this gives this generating function. If I construct this generating function after I know all these invariants and so on, this is not interesting. But the situation is just inverse. It is possible to construct just from knowing the group itself, to construct this generating function. And this was done by Molin at the end of 19th century. He proved this general formula known as Molin series, which allow exactly to find this function which gives, after making formal power series expansion, the number of tensors of given degree in the form of generating function. Here, what we need to know to construct this, to make calculation for concrete example, is the here I introduce the matrix of different symmetry elements, matrix representation of different symmetry elements. T here is formal variables. The sum is over all elements in the group, and this is the character of the final representation, complex conjugated, to be precise. If I need to look for invariant, the character is naturally just identity, so it will be 1. This means the order of the group. This is the formula which make at the first view make rather complicated because you need to know this matrix representation, but in fact it is not so complicated because there are some simplifications which are more or less obvious. First of all, it is not necessary to make the calculation of the whole number of elements. It is sufficient to make the sum over the classes of conjugated elements because they are the same. After that, instead of looking for the matrices, complete matrices, it is just necessary to know, for example, eigenvalues of these matrices. And even if you are more like to use character, it is possible even to calculate this determinant in terms exactly of characters of a reducible representation, just making some kind of symmetric power of this representation, and this is completely expressible in terms of this character, which for most simple groups, especially for all point groups and symmetric groups, this information is quite easily available, so there are no really big problem to make this kind of calculation. But the more interesting is not the making just the numbers of invariant. It is interesting to find invariants themselves. And the idea of this Mollin function is in the symbolic interpretation of the so obtained function. First of all, this Mollin function is a rational function, which always for finite group can be represented in the form like that, where you have the denominator, which is always written as a product of 1 minus t some power. Number of terms here, by the way, is equal to the dimension of the representation. This is so-called algebraic. Each term here describes algebraically independent invariant of the group. And in the numerator, we have some linear combination, or some combination with coefficient, with positive coefficient of this polynomial. And this symbolically means that we have auxiliary invariant of certain degree given by degree this auxiliary variable t, and m means that we have several auxiliary invariants of the same degree. There are some rather simple groups, so-called group generated by reflection. By the way, this group, which is group of the total symmetry of the cube, is group generated by reflection. And in this case, for any group generated by reflection, for invariant, the numerator is just 1. We have only denominator. This interpretation can look like that. This is in some way generalization of my simple presentation here for even and odd function. Arbitrary polynomial invariant can be written as a polynomial of invariant which correspond to these terms presented in the denominator of the Mollin function plus arbitrary polynomial of this invariant multiplied by certain invariant which correspond to the numerator and which has this kind of representation. So we have in some way model of invariant. This have polynomial, arbitrary polynomial of main invariant, and we have some kind of model structure where this auxiliary invariant form the basis of this kind of model. This structure is always exists for finite group. It is proved that for finite group this kind of structure exists for invariant and for arbitrary covariant also, but this interpretation is less obvious for continuous group. But in any case, we should be accurate with giving this kind of interpretation, because it is clear that if I know that there exists some system of invariant polynomial which are algebraically independent and some other polynomials which are auxiliary linearly independent, I can write immediately this kind of function which will give exactly the Mollin series with the numbers which are needed. But if I go in reverse way, if I find this function initially, but I want to interpret it, I need to be careful with constructing this function, because sometimes some cancellation can occur between numerator and denominator, and there are some problems which symbolic interpretation is relatively complicated cases. It is possible to give completely different interpretation of this Mollin function written initially as a rational function. Instead of looking at this Mollin function as function describing algebraically independent invariant, a linearly independent invariant or covariant, I can look for generators of the algebra of invariants. So I can look for all monomials from which I can generate all the possible invariants. But in this case, when I will take, for example, if I have something like here, the generator, it is clear that there should be included, x should be included in terms of generator, because this is t squared. And normally in Mollin function, the number of terms in denominator, when we want to interpret this Mollin function in terms of generator, exceed the dimension of the problem. But in this case, this invariant becomes dependent. And then, so the numerator in this sense describe the dependency between this generator, which are normally dependent. And this dependency, the dependency of the first kind, we find some dependency between this generator. After, among this dependency may exist another kind of dependency, and so on. This construction, and mainly due to Hilbert construction, the relation between generator is named syzygy in invariant theory, and I will discuss example slightly later. But I want just to show some useful method to construct Mollin function for rather complicated representation, starting from simple representation, from a reducible representation. Very often we need to construct, to look for initial representation as initial representation, reducible representation. And so we can just work with generating function, with Mollin function, by constructing more complicated object. The construction for generating function, if we want to construct tensor of different type, is quite trivial. This is just the sum of generating function. It's quite clear. But less evident maybe the construction when we want to start with reducible initial representation, which is decomposed into a reducible one. But in this case, we need just to make the product of Moline function. This is series which include this coefficient which describe just how many times this final representation is in the product of these two initial representation. So initial intermediate representation F1 and F2. So we need to construct, we need to start, we can to start from Moline function for purely irreducible representation, and by coupling of this kind of procedure, we can construct any function for more complicated representation. And even this procedure is rather useful from the point of view of constructing the basis of invariant covariant, because this construction gives immediately how to construct for more complicated representation the basis, so-called integrity basis, if we know the basis for simpler representation. This is just an example, for example, for OH symmetry group. This is initial representation, it's three-dimensional our space, so three-dimensional representation which is naturally irreducible representation because we have all these C4 axes which transform X to Y and Z. So we have three terms in the denominator which are just X squared, Y squared, Z squared, which is evident. This invariant, this another invariant, third invariant of degree 6. But just to remark that if we look at the symmetry group, which is not the complete symmetry group of the problem, but just the subgroup, which include only rotations, so-called O group, not OH group, but O group. OH group is product, direct product of O group by inversion. But for O groups, this group is not groups generated by reflection. And in this case, we have another auxiliary invariant of degree 9. And you see this in this generating function. And this gives that arbitrary polynomial, invariant polynomial with respect to this group can be written as polynomial in this 3 invariant plus this one multiplied by another polynomial of this 3 also invariant.
May I ask a question?
Yeah?
Could you please go back?
Yeah?
First? In this case, it's clear that phi 9 squared can be expressed via thetas.
Yeah.
And it's clear that for point groups, more or less, it always works like that. But is it general case that these invariants, which are in numerator squared, can be expressed in the basis of denominator invariants?
About square, I'm not sure. I just discussed with Rainer this question.
I see. So yeah, I'm not alone.
Yeah. I'm not sure. I have not found, I wanted to find an example where we have something more complicated, not square, but degree 3 or 4 expressible in terms of basic invariant. But I have not found just for yesterday, during yesterday or today. But I do not know that if this is right or not. But for many cases, this is like that. Example which I suggested that I know that it is possible. It depends also because you see the choice of numerator invariant is not unique, especially in the case you have several invariants of the same degrees. So if, for example, you have two invariants of auxiliary invariants of the same degrees, I give just to Rainer this example with icosahedral group. Icosahedral group which to construct invariant from the initial representation of dimension 5. This is H representation. There are 5 terms in the denominator, but in numerator you have something like you have 2 auxiliary invariant of degree 6 and 1 auxiliary invariant of degree 12. I am pretty sure that by making some linear combination of the auxiliary invariant, they are defined up to linear transformation naturally, I can make the choice in such a way that I will have one auxiliary invariant whose square will be T12 auxiliary invariant, and x4 degree will be expressible in terms of basic invariance. But I'm not sure that probably another choice will give another possibility, but probably it will be a linear combination of basic invariant plus auxiliary invariant. And in this case, only degree 4 will be expressible in terms of basic invariance. But this is just my trying to answer this conjecture. And, I have not really verified, but this is kind of groups for which it is possible to check for counterexample if you want to this conjecture. But I did not want to say that there is counterexample. I don't know.
Just before we finally leave that story, yeah. I mean, if you go back to your slide earlier, you had a description, a general formulation of the ring structure, which says that any well, we can keep this page. That one there. So any polynomial invariant can be written like this sum. So in this example,
in this case, this is polynomial of 3 invariant.
Yeah. So in this example, it would say that any invariant can be written as a polynomial in the thetas, and then plus the single phi times another polynomial in the thetas. And therefore, in particular, phi squared can be written in that form.
Yes.
So this means that, therefore, phi, in fact, satisfies a quadratic equation in terms of the others. So that suggests to me that if you change your coordinates in some way, you can...
No, but you speak that in some way, if we have one auxiliary invariant, it is clearly that its square should be expressible.
If it's more, then it's not...
But if you have several...
Right. Yeah, not so easy. Yeah.
Not so easy to say that it is possible also to make expressible.
So maybe in this case, yes, but...
This is just a concrete example of this kind of syzygy in this case. I simplify by putting theta squared to equal to 1. But this kind of relation is quite important if we go now to geometric representation of the space of orbits. First of all, I remind you that there are several different kind of orbits. This is C4 orbits, this is C3, this is C2, and there are 2 kind of different planes which are not conjugated. This is planes which go through 4 middle of edges in this one. They are not equivalent. So there are different kind of representation, and this is the representation of the space of orbits in the space of invariant polynomials. It is important that invariant polynomials separate orbits. So I can just plot in space for this group. I have just basic invariants which are algebraically independent. So I restrict, to make simpler the picture, on the surface of the sphere, because naturally this is foliated by the spheres. I can look what happens with one sphere, and I have two algebraic independent invariant, and this is description of the space of orbits on this action. In this space of orbits, the boundary of this space of orbits is exactly this CZG, this one, because the square of auxiliary invariant expressible in terms of basic invariance, and if this square is equal to 0, this gives just the boundary for the space of orbits. Here the auxiliary invariant, or for OH, this is not auxiliary invariant, this is covariant. This is equal to 0, so this gives just the boundary of the space of orbits. Orbits correspond to the points inside and to the points on the boundary of this space. On the boundary we have CS orbits. Inside, this is generic orbits. If we, for example, go to the... I want just to show what can be done useful, this is space of orbit. As soon as we are interested in some invariant function, we can express also invariant function as a function of our invariant polynomials. And normally we always work with some polynomial expansion. For example, if I'm interested in this case in some polynomial expansion of invariant function, I can write it in terms of two invariant of degree 4, degree 6. If I, for example, limit to degree 6, this will be just a linear function of invariant. Linear function, and levels of this linear function will be just straight lines. So if I have now any object, for me this is Hamiltonian, for example, or any other function, potential, depending on parameters, I just move this line corresponding to the level of this function, and I look at the intersection with this orbifold. And I see that there are some critical orbits. The critical orbits are just these 3 points, which correspond to orbits isolated in their strata, and this is just zero-dimensional strata. And these points correspond always, or stationary points of any invariant function. This is very useful theorem proved by Louis Michel and by some other, Palais and so on, discuss the same problem, but the application is quite important. We know that if there are some critical orbits of the group action, these points will be always stationary points of any invariant function. So if I look, for example, invariant function, I look at different sections. When I go through these stationary points, I have stationary points at this value of invariant function. For example, if I will change this combination, linear combination of the invariant, sometimes I will have stationary function, just for example 3 stationary functions. Sometimes I will have more than 3 because, for example, here we have some critical behavior related with touching of the boundary. So we have appearance of the new kind of stationary point.
I don't understand this picture. Could you just explain slowly why if I take a point from this interior, how I get from that point to a corresponding orbit? What does it mean to say that?
Just a molecular example, which is quite simple. This corresponds, for example, the action on the sphere corresponds to a description of rotation of molecules. The Hamiltonian should be invariant with respect to this symmetry group. So I can write my Hamiltonian as a polynomial in invariant. This will be the polynomial in theta 2 and theta 1 of 4 and 6 degrees. The level of the Hamiltonian is just a straight line. This is linear function. The Hamiltonian is linear function of 2 invariant. So the Hamiltonian, this level pass through these stationary points. This means that at these points we have stationary points of this function on critical orbits.
So where's the orbit? How do I get the orbit from a point in that?
We have invariant function defined on the sphere. There are some special points which have exceptional symmetry. C4 points, C3 points, and so on. Around these points, all surrounding points has different symmetry. So these points are isolated by symmetry. The theorem states that if the point is isolated by symmetry, it is always stationary points of any invariant function. So I write any invariant function, and I have stationary points at C4, C3, and C2 axes. So I have at least 6 stationary points on C4 points, because the orbit is order 6. I have 8 stationary points which correspond to the C3 axis, because there are 8 points on the sphere. This is orbit of C3. And I have 12 stationary points which correspond to local symmetry to stabilizer C2. So my generic Hamiltonian function always will have at least 26 stationary points. Among these 26 stationary points, 6 correspond to C4 stabilizer, 8 to C3 stabilizer, 12 to C2 stabilizer. But depending on the number of the relation between parameters, for example, if levels of my Hamiltonian function, energy function, or any function, is just like that, when I move, the topology of this section does not change. So there are no reason that I have here some stationary points. Only when I go through critical orbits, there are stationary points. But for some special relation between parameters, for example here, I can have the special value which correspond to modification of topology of the levels of the function. And this will exactly correspond to appearance of additional stationary points.
I understand. So if I take a point in the middle there, that corresponds to a value of, is it theta 1 and another value of theta 2? Is that right? So then how do I go from that pair of values, theta 1 and theta 2, to an orbit?
This is coordinates. The polynomial here just coordinates of these points. Instead of looking at the whole sphere, I look just at the part of this sphere, because I look on the orbit space. And my polynomials gives just the coordinates on this part of the spheres. I can later example. Maybe here it's better to see. This is different kind of stratification of this cube. If we look at the sphere, you will see this kind of points which correspond to. Normally, orbifold is just representation of this elementary cell in another kind of coordinates, in invariant polynomials. By invariant polynomials, I parameterize all the points of these cells. And the first statement is that because these 3 points are critical, they are always stationary points of any invariant function. But to look if there are additional stationary points, I can obtain some additional information by looking just at the level of this function in the invariant polynomial representation, because level of function, for example, if I restrict by 6 degree, is quite simple, it's just linear. And I can look if there are some additional levels which correspond to appearance of additional stationary points. If, for example, additional stationary points appears on this stratum, I know that there are 24 equivalent stationary points because this is orbits of order 24. So this is some kind of using this.
Excuse me, but I also can imagine that having a polynomial of relatively high order,
Yeah.
I could equally well to have extrema in the middle of
Yes. But this is also interesting conclusion because you can look what kind of degree of polynomial you need to have points at the, for example, for this example with cubic symmetry, for example, for 8 degree, you can even prove that there are no inside.
Okay,
There is only on the
I
boundary.
agree that if I have linear minimization, so to speak, or extremization, if you like, then of course
Yeah.
the boundaries are the most important, especially the critical points. But that's
Yes,
only
but for
in the
higher
lowest order.
for higher degree, surely you can have extrema anywhere. But you need to go to very high degree.
Can one generally prove that the largest isotropic groups are always at the critical points of the order parameter, for instance?
Generic orbits is just the
Generic is inside.
yes,
of course.
inside.
Of course.
Yes,
But say,
but you can have isolated point. It depends. If you take, for example, the group not OH, but just group O, in this case, this is just example. Here, to represent O group, you need use not just two algebraically independent, but also auxiliary invariant. And you can distinguish 2 points just by sign of this auxiliary invariant. So the space of orbits in this case will be represented by 2 parts of this OH orbifold, but the points on the boundary should be identified because they correspond to the 0 value of auxiliary invariant and they are the same. And so the form, topological form of the orbifold in this case will be the sphere. The sphere with 3 exceptional points. So if you want here, you will have generic point, but isolated point inside with higher symmetry.
But maybe the question was about the stabilizers.
Yeah.
What can you say about the size of the stabilizer from this kind of geometric structure?
The size, not every subgroup can be generically as a stabilizer. There are some specifics. Only part of the subgroups can be can appear as a stabilizer, but there are no, as I know, general answer of the question what kind of stabilizer appears. But you have nature of some kind of lattices between stabilizer and organization of the strata by their stabilizer.
Yeah, so
This
there's
is
some kind of
some
isomorphism between
ordering.
strata structure.
Yes.
But maybe the question is whether you can identify the stabilizers corresponding to your edges of your space. I mean, to these extreme points. Like you have these points C2 nu and C3 nu, and there you have always.
No, but just I don't understand quite question. The position of the critical orbits,
Yes.
or critical orbits, depends on the group action.
Yes,
This
sure.
is group action which describes the stratification.
Yes.
After that, I have invariant function, and I look for stationary points of invariant function. And I can say only that for isolated critical points, I will always have stationary points. If
they are
that,
always at the border.
no, No,
Oh, they could be inside also.
just example with all groups, they're inside, there's no boundary.
That's very bad.
No boundary. But even when you have boundary, there are simple example of point group where there is boundary and point inside. So there are many examples like that.
So it depends upon the invariance that you put.
Yes,
on the axis.
this is depends on the structure of invariant, of the algebra of invariant.
You didn't include the third one here. You actually should include phi.
No, but just number 1 and 2, but degree is 2, degree is 6 and 4.
Yeah, but you also have, if I remember, can you please to go on? Oh, no, one more. One more. Oh, yes, here. You have
This is 9 degree.
Okay,
This is
yeah,
4.
The three
Full-
thetas.
Okay, so you just normalize everything to theta 2.
Yes, yes.
Okay, you are on the sphere.
When I go to the sphere, this is 1 and I look for this 2.
And is it clear that phi 9 squared gives you a border?
Yes.
I don't see it immediately, but okay. So,
But phi 9 squared
okay, I understand that I can express them
should be greater than 0 or equal to 0. It cannot be negative. Is it
Yeah.
clear?
yeah,
That's all. So
okay.
this is expression in terms of basic invariance, which when I make the square, when I
Okay,
go
so
to
we are
this,
in this fortunate
this
situation that we have syzygy relations.
this is syzygy. So this is expression should be positive or 0. So I look for the region where theta 4 and theta 6 satisfy this relation. This is greater or equal 0.
So I am inside this area,
Yes.
degenerated.
Yeah.
But,
But the boundary is just 0 value of this.
which I don't know
Polynomial?
whether it's fulfilled.
Huh?
I'm not sure whether I find a place where this is precisely 0. I have inequality.
You have an equality, but it is possible that 9 0 square is 0. It is possible.
Always. In
It's,
this case, I believe, but is it always true that syzygy gives you a borderline? Well, so later. Then.
I cannot generalize to,
No.
because after we have some syzygy of different kinds and so on, it's more complicated situation. But if you have just one auxiliary invariant, it's quite clear.
But you mentioned that there is a recent book by Eisenbart and others called I think you said it was called The Geometry of Syzygies.
Yeah.
So maybe this contains the answer
Oh,
to
okay.
all questions.
Oh, this is just example. I will miss it. I want just to, probably I need to finish. I want just mention some other interesting point related with generating function, just to show that when we look at this expression, sometimes it is quite important to know what is the behavior of this coefficient as a function of n. Normally, we can calculate the development on Taylor series by Maple. It's do rather well and so on. But it is interesting to see what are some kind of generic behavior of this coefficient as a function of n. And normally, we can give this kind of answer. First of all, this behavior of this coefficient as a function of n include purely polynomial part and oscillatory part, which correspond to periodic function. This kind of object is named quasi-polynomial, and the period of oscillatory function depends on these exponents. I put here just simplest with 1 in the numerator, but an explicit expression for this coefficient include rather strange initially object taught polynomials. This means this taught polynomials appears in some kind of topological interpretation of different kind, and this is taught polynomials expressed in symmetric function of this exponent, and we can, this is expression for a regular part of the polynomials. But another most curious fact is that if you look at the oscillatory part, this oscillatory part in some way described by the same kind of the taught polynomial, but in this sense that we have a series of this taught polynomial which describe the behavior of oscillatory part. This is a rather complicated example with arbitrarily chosen numbers 3, 5, 7, just to see rather complicated behavior, but nevertheless this
So
is...
what do these dots represent?
Huh?
What are we seeing here?
Dots represent this oscillatory part addition. This coefficient is polynomial plus some modulation. This modulation, the period of this modulation is equal to the product when they are mutually sample product D1, D2, D3. So this is oscillatory function which goes to 3 multiplied by 5 multiplied by 7, 105. So this is 0, 105. This is period of this oscillatory function. This is value of oscillatory function. So I just put for this 105 because it's periodic. But on this interval, you see this is rather peculiar behavior in any way. But this peculiar behavior is described by the same, this what is plotted here is just the polynomial, the same taught polynomial which explain the behavior of the regular part. So this is some kind of rather curious behavior. And this is some kind of geometrical representation. By the way, this is schematic representation of the space of orbits for OH group on the sphere, if you want, with 3 specific points on the boundary. But if you go to the O group, you need to take to this object, to disk, and glue them on the boundary, and you will have a sphere with 3 points just surrounded by generic points. This is just representation of the space of orbits for O groups. This is some kind of representation related with symmetry group for periodic crystals. Just example which I've taken is example of OH group, the body-centered crystallographic lattice. And a lot of different strata with different local symmetry groups. And if you go, for example, for the space of orbits, you need from elementary cell also to take some part of this elementary cell. All other points are obtained by the group action. But this part elementary cell is some specific behavior because you need to identify, for example, part of this on one of the boundary of this tetrahedral. And for example, in this case, the space of orbits, a rather peculiar object. This is 3-dimensional object which can be imagined as gluing to, just superposing 2 cones one on another, this big cones, and inside there's stratum which is specific symmetry. You have some special behavior, some isolated points inside with another symmetry which form this one-dimensional subspace. And there are many different examples. I'll just take one. Well, I think it's time to finish. there's some kind of generalization of a notion how to apply not just to function, but for more complicated objects like matrices or like matrices defined over some spaces, equivariant ways, and in this case the qualitative description also is based on the same kind of analysis, how we can distinguish in the space of complex control parameters, how we can distinguish different regions which correspond to different type of dynamical behavior, different type of some stationary system of stationary points, or existence of some another invariant. In the case of this matrix representation, some kind of Chen numbers may be characterized by eigenbundles of these matrices. And so this is also, all that can be done in the scope of this invariant theory application. Sorry, I probably started by too trivial example, but the idea was just to start some kind of probably discussion, further discussion with models more appropriate for.
Well, I'm sure you've succeeded in doing that. Thank you very much. Any questions? More questions?
I mean, in liquid crystals, we typically have continuous groups acting rather than finite groups. So what about you said can go over to that kind of context?
But in principle, invariant theory, it's working for continuous group as well.
Yeah, but I mean, things like this Molian theorem presumably have.
Yeah, the Molian theorem, you replace the sum by integral over integral measures.
But then what does it mean? Because you would write sort of orders or something.
But it still counts the numbers of invariant, independent invariant functions of different degree.
You get the same kind of description in terms of Molian series, but there I can just give an example which shows clearly the difference between finite case and continuous case. For example, we can take SO2 group, which is the simplest continuous group, just one parameter. And I can take as initial representation the representation 1 minus 1, which corresponds to the function transforming according to m equal 1, plus minus 1.
So it's a four-dimensional.
This is two-dimensional representation, initial. How you prefer to label a reducible representation of SO2? The abelian group which has one-dimensional representation. So I take as representation, for example, this representation. I can ask what is the number of invariant or number of covariant of any types constructed from this initial representation.
So what do you mean by the minus 1 representation?
Plus minus 1?
Exponent I phi and exponent minus
Yeah.
I phi.
Oh, I see. Okay, just forwards and back. Yeah.
Are these matrices or what are they?
Yeah.
You have just, if you consider not SO2 but O2, in this case you have two-dimensional representation, which label by 1, but you have two lines. And if you make the reduction to SO2, this decomposes in plus minus n. So this is one-dimensional representation, complex representation of this group.
Yeah, one complex dimension. Yeah.
Yeah.
So it's a real four-dimensional representation.
No. This is real, this complex character. But if you look at this representation from the real point of view, it's two-dimensional representation. That you can decompose it that the two representation plus minus 1, this character
M5. I
uh, for m equal 1, this is 1 for, and this is just a reducible representation. And you can construct, instead of this representation, you can construct multiple representation of higher dimension. And if, for example, I have just this. For example, I will take n equal 2, and I will construct the invariant of type 2 of this group, of covariant of type 2. Not invariant, but covariant. The Morin function will have the following. Just to see why 3 here, because we have 4-dimensional representation. This is 1 plus 1 plus minus 1 plus minus 1. This is 4-dimensional representation, but the group is continuous, so the space of orbits has 4 minus 1. This is 3 basic invariant we have. All these are quadratic. But as numerator, we have something which is not positive. Which is not positive and cannot be turned to be positive. So we cannot interpret in this case the structure, in other words, from the more mathematical formal words, this model of covariant is not free. There's some kind of relation. For finite group, for any covariant, I can always transform this function to this some kind of denominator multiplied by numerator with exclusively positive coefficient. So there are no relation. There are 3 models of covariance, but here it's not free.
So I don't understand notation, but let maybe still ask a question. But I mean, so for example, in liquid crystals, you have functions depending on second order and third order tensors. So is there an algorithm for calculating, say you're interested in variant functions of second and third order tensors, and the rotation group is acting on this as a group. So is there an algorithm for constructing this modular function which will give you everything about the invariants in this case, or not?
But from the point of view of constructing, if you have initial tensor of some kind, you can construct polynomial just by making the tensor coupling using Clebsch-Gordan coefficient for this group. You construct higher and higher order terms, and no problem. The problem is just to check if the different coupling give independent or dependent terms in each degree, how many we have independent terms. Finally, you can construct all the polynomials in given degree, make the projection, and check the number of independent terms, and you will have this information. This can be done in straightforward way for any group by just this standard Clebsch-Gordan procedure, coupling of tensors of given degree. The Morin function is interesting because it allows to calculate for arbitrary order the number of these terms which are present and give the way to construct in this polynomial of invariant function plus auxiliary, linear auxiliary multiplied by this. And this is using, if this structure is working, it is quite good way to construct all polynomials in any degrees, knowing this basic and this auxiliary invariant. But it turns out that this is not does not work for continuous group. This is example of SO2 group. For covariant, naturally, you have no these terms. You have only this auxiliary polynomial, which is covariant multiplied by arbitrary polynomial. This will be invariant polynomial. This will be the system of covariance which we will have. And so here, this shows that this does not work for this covariant.
Because it's a reducible representation, that's why.
Here, this
If you have irreducible, you don't have these problems. At least I didn't.
no, but for finite group, you have not this problem even for reducible representation.
I see.
So this is, for finite group, it's not important. Your representation is reducible or irreducible. Here I have for reducible representation, it's sufficiently big reducible representation. But more interesting situation is that formally I can here give some symbolic interpretation of this description if I transform this function in another way. You can check that this is just identity. So in this way, I can use this representation and I can say that all the invariant, all the covariant, I can write at this 2 second-degree covariant multiplied by all polynomials of 3 basic invariant. And this covariant, one covariant of degree 2 multiplied by all invariant only of 2 among 3. So this is different kind of structure. This model is not 3, but this is interpreted in terms of this concrete simple group, but it's quite possible that this can be generalized for more complicated example. But what we have just example, rather elaborated example with SO2 group, which shows that this kind of interpretation is working, but the rigorous mathematical background on that, we have not found any mathematical description of that.
Okay, thank you very much, Boris. Thank you, Boris.